start with your physics class, that is your class 39 that we have to discuss here. In the last classes we had discussed many more topics, that is your Aristotle fallacy, Newton's first law of motions, as well as their numericals, and many more we had done. Now in today's class we will start discussing about the conservation of momentum, that is the important one. So stay tuned with us and please like, share and subscribe so that many and maximum people can get the information at once, and you can also enjoy the video as well. So let's start it with the same, that has been the very important one, and please stay tuned with us so that you will get all the information related to it and in an easy way. Other than that, we are dealing with many of the subjects related to it. You can go ahead. We will start discussing about the conservation of momentum. Conservation of momentum. In conservation of momentum here, the second and third law of motion that led to an important consequences, the laws of conservation of momentum. Take a family example. A bullet is fired from a gun. If the force on the bullet by a gun is 4F, the force on the gun by the bullet is minus F. It is in the opposite direction. So according to the third law, the two forces act for a common interval of time, delta t. According to the second law, F delta t is the change in the momentum of the bullet and minus F delta t is the change in the momentum of the gun. Since initially both are at rest, the change in the momentum equals to the final momentum of the gun, and since initially both are at rest, the change momentum equals to the final momentum for each, where thus B we can say that that is the momentum of the bullet after firing, and PG is the recoil momentum of the gun. So it is, we will state that PG equals to minus P2, or we can say that PB, ये जो आपका PG है, ये PG ये है और PB इधर आ जाएगा, प्लस PG equals to 0. That is the total momentum of the bullet plus gun system in the case that is being conserved. Okay. On the same way here, that thus is an isolated system, that is the system with no external force, mutual force between the pairs of particles in the system that can cause momentum change in individual particles. But since the mutual forces for each pair are equal and opposite, the momentum change that is cancels in pair and the total momentum remains unchanged. This fact is known as the laws of conservation of momentum. On the same way here, that the total momentum of an isolated system of an interacting particle is conserved. So I just write it down for you all. You can write it down. The total momentum of an isolated system of interacting particles is conserved. So an important example of an application of the law of conservation of momentum is the collision of the two bodies, and you have to consider the two bodies A and B with initial momentum PA and PB. The bodies collide, get apart with final momentum P dash A and P dash B respectively by the second law, and on the same way it will be P delta AB delta T equals to P dash A minus PA and F dA delta T equals to P dash B minus P, where we have taken a common interval of time for both forces, that is the time for which the two bodies are in contact, and since FAB plus or minus FBA by the third law. So P dash A minus PA plus or minus P dash B minus PB, that is P dash A plus P dash B equals to PA plus PB. This is what we have, and here for which shows that the total final momentum of the isolated system, that is equal its initial momentum, and that notice that this is true whether the collision is elastic or inelastic. In elastic collision, there is a second condition that the total initial kinetic energy of the system equals to the total final kinetic energy. Now we'll discuss about the equilibrium of a particle, that has been the important one. So here we go for it, and equilibrium of a particle basically stands for a particle in that mechanics that refers to the situation when the net of the forces is being take place. Other than that, if I've just told you some of the questions related to it, so that we will cover up that as well. So we'll cover up the 10 questions today, and then after that 10 to the in each and every class of the remaining classes will be covering all the questions regarding this. So first question for the same, it will be first, the simplicity in the numerical, you have to calculate the G is equals to 10 seconds inverse square. So for that, give a magnitude of a direction of the net force acting on. So that your first part for this we have a drop of rain falling down with a constant speed, a cork of mass 10 gram floating on water, and a kite skillful held stationary in the sky. And another is the car moving. Okay, I will be let you write all these type of questions so that it will be helpful for you to solve by your own, and that is being very important as well. So for that sake, I just go for the questions. There are many questions in it, so I just told you about that. A kite is skillfully held stationary in the sky. A car moving with a constant velocity of 30 km/h on a rough road, and a high-speed electron in space far from the mole material and free of electric and magnetic field. The another question is a pebble of a mass of 0.05 kg is thrown vertically upward. Give the direction and the magnitude of the net force of the pebble here, and that on the same way. It has been first is during its upward motion, second is during its downward motion, and the third part is at the highest point where it is momentarily at the rest. And you also change if the pebble was thrown at an angle of 45 degrees without horizontal direction. You have to ignore your resistance here. Another question is the third question, give the magnitude and the direction of the net force acting on a stone of a mass of 0.1 kg. First part is just after it is dropped from the window of a stationary train. Second is just after it is dropped from the window of the train running on a constant velocity of 36 km/h. C is just after it is dropped from the window of the train accelerating with 1 meter second inverse square. Lying on a floor of a table which is accelerating with 1 meter second inverse square, and the stone being at rest relative to the train. You have to neglect the air resistance throughout. So the fourth question for the same, which will be have is your one end of the steering length L is connected in a particles of mass M, and the outer to the small peg on a small horizontal table. If the particle moves in the circle with speed v, the net force on the particle that is directed towards the center is you have to find out T minus mv square by T plus mv square by L, and that for the fourth case it is you have to find out. Where T is the tension in the string, you have to choose the correct alternative among this. The another question we have is your fifth question, and that will be last question for this session. So the question is, a constant retarding force of 50 Newton is applied to a body of mass 20 kg moving initially with a speed of 15 meter second inverse, and how long does the body take a stop? That you have to do. A constant retarding force of 50 Newton is applied to a body of mass 20 kg moving initially with a speed of 15 meters second inverse. How long does the body take to stop? Now we're going to end up here. So we'll start discussing in the next coming class the rest of the questions. So stay tuned with us. Please like, share and subscribe so that many and maximum people can get the information at once, and you can also enjoy the video as well. Thank you. Keep supporting us as you have supported till the date.